Hello Science Alliance, hello my IGCSE physicists, I am Lara. This is my science education business, Theatre of Science. I like these lessons because I am trained to teach physics to A-level, and my job has kind of pivoted into just teaching home educated people just whatever they want to learn about, like soil or volcanoes or koala bears, but we actually get to do GCSE physics, which I'm excited by. So we'll start the activity. Activity is a bit of a generous word, to be honest, but I need you to cut some paper and we'll do a little recap, okay? And then I'll get you to use the thing that you've made. So for this lesson, it's not an activity, but it's to help your understanding. I need you to get just an A4 piece of paper and cut just a strip off the end, the short end, okay? You actually need 2 strips. What are we doing? This is the lesson because I've taught this whole module before. We're going through the whole IGCSE topic, module by module. There's 8 of them all together. I've taught it all before over the course of 2 years, and now we're in the first year of the second time I'm teaching it. And this is the lesson that I have changed quite a bit because I watched it back and I thought, that was a bit confusing. Okay, so what you're doing is just cutting 2 strips of paper. They need to be sort of the same length. They don't need to be the same width or anything. Don't worry too much. While I quickly recap us on some stuff. So do you remember electromagnetic waves? Do you remember? Yeah? We've talked about how light is an electromagnetic wave, but so are radio waves and microwaves, X-rays, gamma rays. Basically, the only difference between these is their wavelength, right? So from peak to peak, radio waves can be miles long, gamma waves, very, very, very small. And we've learned about the difference between them. But light is just an electromagnetic wave like any other, but it happens to have a wavelength that our human body can detect. And we've talked about how light's a bit vague, isn't it? All different colours of the rainbow mixed up together make white light, but the different colours of the rainbow have different wavelengths. So you could say, instead of just saying light, we'll say all the different colours of the rainbow. Is that okay? Is that all right, what I've got on the board there? Is that okay? So now it goes radio, microwave, infrared, and then violet, green, yellow, orange, red, and then ultraviolet. Is that okay? Hopefully you're shrieking at the screen. No, Lara, that is not okay. It's the other way around. Like that, isn't it? Good. So red, microwaves, radio waves, microwaves, infrared, and then red light has got the longest wavelength and violet light has got the shortest wavelength, and then in the middle, it's in the middle. Okay? Good. So that's part of the recap you needed to get through this lesson. We already talked about this just last week, but I don't think we can recap it enough. Wavelength is the length of one full wave. And it's measured in meters because it's a length. It's the length of a wave. Could be from peak to peak or from trough to trough or from the middle. You go all the way up, all the way down, back to the middle, the length of that wave. So what's the wavelength of that wave? It starts at 0, goes all the way up, goes all the way down again. Okay. Do you know what? This is a very poor question. I changed the graph a bit, and in doing so, I have cut off the x-axis. So actually, the correct answer here, because you've got no labels on any of the axes, the correct answer here is you've got absolutely no blooming idea what the wavelength of that wave is because you don't know what the x-axis is. That could be seconds, couldn't it? And that wouldn't tell you what the wavelength is. But if the x-axis is in meters, then the wavelength of that wave is in 2 meters. Sorry, amateur hour. Yeah, 2 meters, right? One wave, 2 meters long, so 2 meter wavelength. Good. Frequency is how many waves per second. How many waves per second? So here we've got a wave that goes all the way up, all the way down, all the way up, all the way down, all the way up. And that 1 second has gone by for all that's happened. So what's the frequency of that wave? Frequency is measured in hertz. Hertz just means per second. So it's how many waves per second. How many waves here? I have actually bothered to put in time in seconds on the x-axis now. So there's no tricks here. How many waves per second? Well, all the way down, that's 1. All the way up, all the way down, that's 2. So there's 2 waves happening here per second. So the frequency of that wave is 2 hertz, 2 waves per second. And what's the last thing that we've talked about? It's important if you're measuring waves. You've got the wavelength, you've got the frequency, you've got something else. Have you cut your 2 strips? Could you please, the quickest way to do this, put your 2 strips together and then fold them 3 times. Fold the short ends together 3 times. And then fold them out. We're just making it so that there's 8 sort of boxes on the piece of paper divided by creases, yeah? So fold it in half once, fold it in half twice, fold it in half 3 times, and then fold it out again. So you've got 2 strips of paper with basically 8 little boxes in each one, made from creases. Period. Do you remember what period is? What's the period of a wave? Period? Do you remember? What is the period of a wave? Go on. Have a second or two to try and remember. So you've got two little strips that look like that now. Yeah. Good. Period is, frequency is how many waves per second, measured in per seconds, hertz. Period is how long it takes the wave to complete one full cycle. So period is how long it takes the wave to complete a full cycle, so it's just measured in seconds. So what's the period of this wave? How long has it taken for that wave to complete a full cycle? It goes all the way up and all the way down and then comes back to the midpoint again after 2 seconds. So the frequency, wow, what do you reckon? What is that? The period of that wave, how long it took to complete one full cycle, is 2 seconds, okay? Because one full wave went by in 2 seconds. Okay, let's have a little play with this bit of paper to try and understand some stuff. The last thing you need to do before you use this paper is you need to turn the little strips of paper into a concertina fold. You know what a concertina fold is? Oh God, I don't like describing crafts on bit of science. So you've got some little creases there separating out that you've just made, separating out the boxes. You need to fold the piece of paper down one side, down one way, and then fold it along the other way, and then fold it one way, and then fold it the other way, and then fold it the other way. I'm showing you on the screen. So you end up with like a little concertina. I've done something very wrong. I don't know what. There we go. Okay, so you ended up like with a zigzaggy bit of paper, and you need to do that twice. Yeah? Strangely pleasing. So what we're going to use this for is we're looking today at the relationship between the speed of a wave, which isn't something that we've really talked about before. We haven't ever put a number on the speed of a wave, and wavelength and frequency, because they've got really interesting relationship, and that's what we need to explore. So true to a bit of science form, I'm not really going to teach you anything. I've made you make these little bits of paper, and now I'm going to just give you some questions and see how you do. So if you've got the pair of scissors on you still, can you just put it on a table or on the carpet, something flat, put the point facing downwards. I've said it's a pen on the screen, but it doesn't matter. Let's use scissors. I want you to imagine that this little piece of paper that you've made, just use one of them for now, is a wave, okay? So if you make it start by coming downwards, it goes all the way down, all the way up, so that's one wave, all the way down, all the way up, that's 2 waves, all the way down, all the way up, and then all the way down, all the way up again. So this is your kind of chunk of wave. What I want you to do is put it on the table. We'll say that the point of the scissors is our point. Can you make your wave, your whole bit of wave that you've got, pass the point in 1 second? You don't need to actually do it in 1 second, but let's imagine that this wave is travelling along and it passes that point, this bit of the wave passes that point in 1 second, okay? I think it'll help you if you've actually got this set up in front of you. So it takes 1 second for all those waves to pass that point, okay? That's where I need you to be at. And then see how you get on with these questions. Some of these questions are very difficult. Don't forget, I mean, some of you are like 16 and about to do, well, actually, you've probably just done them. Some of you might be actually seriously thinking about doing IGCSE physics really soon, and some of you will just be watching these lessons for fun. So I don't expect you to answer all of these questions. Some of them are designed to be easier than others. So first question, can you please imagine that from trough to trough or peak to peak is 2 meters on your model? We'll just say that that's 2 meters, okay? So move the paper so that it travels past your scissors or your pen or whatever in 1 second. Can you tell me how many wavelengths on your paper? Be really careful with units here, please. By units, I mean like meters, seconds, hertz. Be really careful with the units. How many wavelengths on your paper? What is the frequency of your wave? So how many waves per second? What is the period of your wave? What is the speed of the wave? So speed is measured in meters per second. And then if you finished all that, this is where I thought that the second bit of paper might be useful. If we double the frequency, but keep speed the same, what happens to the wavelength? And if you've done all that, can you write an equation linking wavelength, speed and frequency by thinking about the answers? So those two are sort of designed to be quite tough. Good brain exercise for you. How are you doing? Should we go through the answers? Yeah? Okay. How many, I don't need you to have finished them all. How many wavelengths on your paper? Did you get that the answer was 4? And what did you put for the unit? I said to be careful. It's not meters, is it? It's not 4 meters. That is not, because it's just how many wavelengths. So it's just a number that you need there. There is no unit for that. What's the frequency of the wave? How many waves per second? Well, it's 4. If you're moving that past that point in 1 second, you've got 4 waves passing a certain point per second. So it is 4. And this time your unit is hertz, which means per second, right? What is the period? Okay, so period is how long it takes a wave to complete 1 full cycle. So if you've got 4 waves going past a point in 1 second, 1 second, then you would just need to divide that by 4, right? So 1 wave must be passing that point in a quarter of a second. And it is, that is the answer. 4 waves in 1 second, so 1 wave takes a quarter of a second, so it's 0.25 seconds. What's the speed of the wave? Well, speed is measured in meters per second. So the speed of the wave, how many meters are passing a certain point per second? That's why we had to say that our wavelength was 2 meters. So it's 8 meters are passing that point per second. So the speed is 8 meters per second. Is that right? Okay, if we double the frequency but keep the speed the same, this is why I thought it might be useful for you to have another little wave made. I made a right hash of this on Facebook yesterday because I was trying to hold both bits together whilst filming it, which didn't work. So I've sellotaped both bits together. If we double the frequency but we keep the speed the same, what happens to the wavelength? All right, let's have a look. So first of all, if I just cover this bit with my hand, this was our original wave, right? Passing this point in 1 second. So we've got double the frequency. We need twice as many waves as that, passing that point in 1 second. But we're not allowed to change the speed. What's going on with that? So I've taken my wave, my second wave, and I've stuck it to this one. Are you okay with the fact that, like, we could change the speed, couldn't we? If we move it twice as fast, then we've doubled the frequency. That's twice as, the first one was 4 waves per second. If we made that really fast, then going past that point would be 8 waves per second. That would double the frequency, but we're not allowed to do that. We've got to keep the speed the same. So what do we have to do to keep the speed the same, but make it that twice as many waves go past per second? We've got to, it's still not working. We've got to make the wavelength smaller. Is that okay? We've got to squish the wave. We've got to squish it. You understand what I mean. I don't have to show you, do I? Please don't make me have to show you. So we have to make it that the paper is taking up the same amount of space as it was before. So now we've doubled the frequency. We've got 8 waves instead of 4 passing this point in 1 second. But in order to do that, we have to squish the wave. You understand. You don't need that. You understand, right? We have had to half the wavelength in order to squish enough waves in. Is that okay? And I said, can you write an equation linking wavelength, speed and frequency by thinking about the answers? Maybe that was quite hard. You could have done what we've talked about a fair bit on Theatre Science now and looked at the units. So we've got speed and wavelength and frequency. And we've talked hopefully quite a bit about how we always think of that as being a number and a number and a number, but there are units involved. And what you do to the number, you have to do to the units as well. So speed is measured in meters per second. I've drawn it like that. That's what that means, meters per second, like meters divided by seconds. Wavelength is measured in meters and frequency is measured in per seconds. So what can we do to the meters and the per seconds to make it equal meters per second? I feel like I've said meters and pers and seconds a lot, so don't worry if you're confused. I am just going to give you the answer. I just wanted to not straight away give you the answer. You might be saying, do wavelength divided by frequency, but that wouldn't work because then you're doing like meters divided by per seconds, and you end up with like meters per second. That's not right. What you have to do is times those together. Meters times per seconds equals meters per second, right? So I had this on the screen actually, but I've jumped ahead a little bit. Which of these must it be? I'll give you a couple of seconds just to look at that. What must our equation be? Is it wavelength equals frequency times speed? Does something per second times meters per second equal meters? Spoiler, no, it does not. It must be this one. Speed equals frequency times wavelength. Meters per second equals waves per second times meters. Meters per second. Right, just to make it even more confusing. Speed, if you ever see the equation written down in a nice catchy little way like this, it'll be V for speed, velocity, equals frequency times, and then this lovely little lambda symbol here, which means wavelength, is used to represent wavelength. Is that right? Is that all right? I said to bring a calculator. I'm going to give you a couple of questions just to sort of get you familiar with that equation and rearranging that equation. And then we'll talk about the fun stuff. We'll talk about why this is a physics lesson and not a maths lesson. And you can't just randomly rearrange things because life doesn't work like that. But have a go at these, first of all. Again, you don't have to try them all. I've tried to make it so that the people who are really confident with maths have got something to think about. Something which you might need to do in your IGCSE. So, wave speed equals frequency times wavelength. V equals F times lambda, and if you want to put it in a little triangle, if you find that easier for rearranging, go ahead. A water ripple has a wavelength of 2 meters and a frequency of 6 hertz. How fast is it travelling? There's no trick questions here, this is just to practice using the equation. The ripple slows down to 9 meters per second. Its frequency doesn't change. What is its new wavelength? The speed of sound in air is 340 meters per second. What is the wavelength of a sound wave with a frequency of 200 hertz? Light travels at 3,000 million meters per second in a vacuum. What is the frequency of a radio wave with a wavelength of 2,000 meters? You had to be really on the ball when I was doing that little recap at the beginning. And if you love maths and you really want some brain exercise, can you give your answer to that last question in kilohertz, not just hertz? And if you finished, sound travels 340 meters in 1 second. So how long does it take to travel? 34 meters. And if you've done that, can you give your answer in milliseconds as well, right? So there's 1,000 milliseconds in 1 second. Have a go at that. And if you've already done it because you're a super maths whiz and I'm not challenging you, well, you'll just have to like and subscribe, won't you? Don't forget to like and subscribe, kids. And if you want to go over to my Facebook page, there is a post on my Facebook page where you can comment if you want, and I will say hello to you at the end. You don't have to. I'm very, very appreciative of the people who just come and lurk. But you do have to like and subscribe though. That's like your part payment for these lessons, and then I'll show you how you can give me actual money at the end of this lesson, because that's how I survive. While you're doing that, I'll draw a lovely kind of unnecessary diagram on the board. Okay, to be perfectly honest with you, I got really into drawing my little picture on the board and I have absolutely no idea whether I've given you too much time or not enough time. Oh, should we go through it? I don't expect you to have got it all done. There's plenty of practice questions like this on the internet if you want more. I'll give you, I don't know, I'll give you a little bit more time. But only a little bit, because I want to move on to the good stuff. This is maths. I want us to move on to putting that with science to make physics. All right, well, hopefully you've got a couple of those answered, so let's go through the answers. Yeah, there's absolutely no trick questions here. A ripple has a wavelength of 2 meters and a frequency of 6 hertz. How fast is it traveling? Well, you do the wavelength times the frequency, so you should have 12 meters per second. The ripple slows down to 9 meters per second, but its frequency doesn't change. What is its new wavelength? So now we need the wavelength. So we've got to do a little bit of rearranging. If you want, you can use a triangle. So wavelength equals velocity or speed divided by frequency. So the speed is 9 meters per second. The frequency is still 6 hertz. So the answer is 1.5 meters. The speed of sound in air is 340 meters per second. What is the wavelength of a sound wave with a frequency of 2000 hertz? Okay, so we've got a sound that the wave, we've got the speed that the wave is traveling at. We've got the frequency, we need the wavelength again, so it's speed divided by frequency. So it's 340 meters per second divided by 200 hertz. Well done if you wrote the units on, equals 1.7 meters. Light travels at 300 million meters per second in a vacuum. What is the frequency of a radio wave with a wavelength? So this was a bit of a sort of, it shouldn't really be a trick question at this stage in the waves module if you've been watching them. You should know that a radio wave and a light wave behave in exactly the same way, it's just their wavelengths are different. So if a light travels at 300 million meters per second, then that's the speed that a radio wave is travelling at as well, assuming it's in a vacuum. So the speed is 300 million meters per second, the wavelength is 2000 meters, and we need the frequency this time, so it's the speed divided by the wavelength, which gives us 150,000 hertz. All right, give your answer in kilohertz. Okay, so, excuse me, there's 1000 hertz in 1 kilohertz, okay? Well, I know some of you just will get this straight away, but some of you won't. There's 1000 hertz in 1 kilohertz. So if I'm changing 150,000 hertz into kilohertz, it's going to be a smaller number. Is that okay? Because for every 1000 hertz, we're just going to change that to 1. Yeah, so it's going to be a smaller number. And what we need to do to get the answer in kilohertz is we need to divide this by 1000. So if you want to divide a number by 1000, where's the decimal point? It's just at the end here. To divide it by 10, you move the decimal point back 1 place. To divide it by 100, you move it back another place. But we're dividing by 1000, so we need to move it back another place. So the answer is 150 kilohertz is the same as 150,000 hertz. Phew. Okay, can we move on? Yeah, is that all right? I'm moving on. I'm doing it right now. I'm moving on. Sorry if you haven't quite jotted those answers down. We've got to press on. We're doing it. We're pressing on now. So if you finish, sound travels 340 meters in 1 second. How long does it take to travel 34 meters? Well, what have we done to get that 34 meters? We've divided, that's a tenth of 340 is 34. So if you've divided the distance by 10, we need to divide the time by 10 as well. So it's 1 second divided by 10, which is a tenth of a second. But if you were going to give that answer in milliseconds, well, 1 second equals 1000 milliseconds. So now this is going to be a bigger number, right? 1 second is 1,000 milliseconds. So if you want to say what a tenth of a second is in milliseconds, yeah, it's going to be a bigger number. And you've got to times it by 1,000. So you start with the decimal point. If you move it forwards 1, you've times by 10. If you move it forward again, you've times by 100. But we want to move it forwards again to times it by 1,000. So the answer was 100 milliseconds. Doesn't matter at all if you didn't get that. I just need to start doing maths out loud in front of you so that by the time you get to your IGCSE physics, you're a little bit more comfortable with it. All right, so we've had a little play around with the numbers, but, oh guys, physics is cool. So when you're doing equations like that in maths, what tends to happen is you just rearrange any little bit of the equation, don't you, to get an answer. So for example, to choose a simple dividing by equals something equation, you might have something like, okay, you've got 2 sweets, or the number of sweets that you have divided by the number of people that you have equals the number of sweets that each person gets, all right? So if you've got 2 sweets divided by 2 people, the answer is 1 sweet each. That's how many sweets people get. And when we're doing maths, you can just go, all right, well, what happens if we halve the amount of people? Oh, if we halve the amount of people, then, oh, I shouldn't have rubbed out the sweets, should I? That would have been super smooth. If we halve the amount of people, then now we've just changed the amount of sweets that each person gets to be 2. But you can't do that in physics. You can't take the equation that links speed and wavelength and frequency and go, oh, we changed that one, then that one changes, because we're talking about real life stuff, and real life doesn't work like that. So we need to talk about what actually changes the speed of the wave and what actually changes when the speed of a wave changes. So you know already what changes the speed of a wave. There's only really one thing, only one thing that changes the speed of a wave. You could say that there's 2. I'm going to keep it simple and say there's just one. What changes the speed? So light travelling through this room. We've done loads of stuff. We've done loads of activities to show that light changing speed. What can you do to make light change speed? You can put it through a different medium. We've talked a lot about medium. Medium is just stuff, basically. So air is one medium, water is another medium, a vacuum where there are no particles, that's another medium. Waves, all waves, I keep saying light, but all waves change speed if they move into a different medium. So light slows down when it hits a medium which is more optically dense, like denser basically. And then if it moves from glass or water, say, into air, then it speeds up. So the speed of a wave changes when the medium changes. To make that slightly more complicated, it doesn't have to be a different medium. It could be like a medium that's changed. So for example, a wave would travel at a different speed through an elastic band that was really loose and an elastic band that was really tight, because you've kind of changed the medium, right? If you've tightened the elastic band. But it's the medium that changes the speed of the wave, and that is basically it. I mean, the temperature of the medium as well. So it travels differently through like warm air than it travels through cold air. But again, you've kind of changed the medium there. So I think we could just keep saying medium at you. Right, so let's get rid of these sweets. So let's say the speed of the wave, this is where you need, again, by the way, oh, I have to break this. You need your little wave back again. We can use this more than once. So we've said that wave speed equals frequency. Can I just write F and a lambda? Sorry, I'm writing backwards, so I'm going a bit slow. Which way? Is it that way? Yeah. Speed equals frequency times wavelength. So if you change the speed, say you halve the speed, say your wave of light hits glass and its speed halves, something's got to happen to one of these, hasn't it? You can't just halve that without anything changing here. So if we've halved the speed, it's got to be frequency that is halved or wavelength that is halved. Which one is it? Now, this is where it gets slightly annoying, because the physics of why one of them changes, we just can't really talk about. It's too complicated, but I did come up with a model, not to explain actually what is happening, but to hopefully help you remember what is happening. If you make a fist, I want you to imagine that your fist is glass. Here's your little wave, if you've still got your paper wave, travelling through air, a less dense medium. When it hits your fist, what happens? Oh, it squishes. It squishes. So this is my model to help you remember what happens. It's not an explanation of why it happens, but what happens when light, travelling at a certain speed, slows down, say the speed halves, it's the wavelength that halves. It's the wavelength that changes. So if that halves, wavelength also halves. It has to do with how the wave interacts with the atoms in the glass, like the electrons in the glass interact, and it has to do with, like, yeah, I'm not going to go into it, but it's the wavelength that halves. And I like this as a little model, because if you put your paper on the other side of your fist and try and show the wave coming out of the glass, it's coming out into a less dense medium, so you can see that as it speeds up, we can sort of say that it stretches. Yeah, it's not what really happens, it's just a memory game, but hopefully that'll help you remember that wavelength, when a wave speeds up, wavelength gets longer. Woof! So it's nothing to do with frequency. When a wave slows down or speeds up, frequency doesn't change. There's only one thing that affects frequency, in fact, which is why I got you to bring this glass of water with you. Only one thing that affects frequency. How many waves per second? Let's have a look. So if you do a little up and down motion in your glass of water, hopefully you'll be able to see a wave. There you go. You can see little ripples, right? Oh my goodness. Oh, this is getting me really excited about the fact that the new Jurassic Park film is out now, and I'm going to see it. I'm actually going to go and see it tomorrow night. I'm so excited. I will be raving about it next lesson. Anyway, we're Jurassic Parking the heck out of this waves lesson. We've got a ripple in a glass of water. What could you do to affect the frequency of those waves? How many waves per second? What could you do? What could you do to affect the speed of the waves? Oh, that's a good question. All right. What can you do to affect the speed of these waves? If you just tap your finger into the centre of a glass of water, what could you do to change the speed of those waves? What could you do to change the frequency? I hope that you're saying, or you agree when I say, there's nothing you can do to change the speed of these waves because you're not changing the medium. You'd have to heat the water up or cool it down, but unless you're actually changing the water in some way, you cannot change the speed of those waves. It's weird, isn't it? You'd feel like moving your finger up and down slower would change the speed of the waves, but it won't. It won't. But you can change the frequency by bobbing faster. When you bob your finger faster, you do change the frequency. And when you change the frequency, you change the wavelength. So if you bob twice as fast, I don't know if you can actually see it. If you go into your exam with a piece of paper and a glass of water, you'll be totally fine for the waves module, won't you? Because hopefully you can see there, very roughly speaking, that if you increase the frequency, if you tap it more, then you are making the wavelength of the wave shorter. Phew! Which again, it matches our equation, doesn't it? If you double the frequency, the speed isn't changing. The speed can't change because it's still water. So if you've doubled the frequency, you must have halved the wavelength. And you have. Right. Right, I'll tell you what, I was going to give you some questions and then tell you about the Doppler effect. I'll switch that around because I want to give you enough time to forget what I just told you before I test you on it. So the Doppler effect also has to do with wavelength and speed. There are two different people that could write your exam, your IGCSE physics exam, Cambridge or Edexcel. We tend to just cover both of them here because they're quite similar. If you know that you're actually sitting a Cambridge exam, you must revise for the Cambridge exam, and the same for Edexcel Pearson, because there's slightly different things that they need you to know. So Cambridge actually don't need you to know about the Doppler effect at all. But Edexcel do. So very quickly, what the Doppler effect is, I was going to show you this diagram. I'm not sure the diagram works. I'm not sure it helps. How can I explain it? So I'll show you I bothered to get the diagram, I'll show you it. It's on the printout. Here we've got a train, and the whistle on the train is blowing, but the train is not moving, okay? So as you would expect, the sound waves are going from the whistle, spreading out in all different directions, because this is a uniform medium, probably air. So that is just what you'd expect. When the train starts to move, something kind of weird happens. So the train gives off a sound wave, but the train is moving forwards. So it gives off a sound wave, but the next time it gives off a sound wave, it's got a little bit closer to the sound wave before it, if you see what I mean. And then, so what happens is the waves sort of appear to be bunching up. And on this side, it's the opposite. It gives off a sound wave, but it's moved forward. So the next time it gives off a sound wave, the crests of those waves are further apart, and the crests of these waves are closer together. So what ends up happening is, in fact, our little bit of paper wave is quite a good way of showing this. If you've got, say, a sports car, a racing car, which is travelling really, really fast and coming towards you, then it's giving off a wave, but then it's sort of almost catching up with that wave. So the wavefronts are really close together. So the wave sort of, when it hits your ear, it's just wavefront after wavefront after wavefront, and it's quite a high-pitched noise, as we talked about when we did the sound lesson. And when it's going away from you, the opposite's happening. It's giving off a sound wave, but then it's travelled further away, so when the next wave comes, it seems to be more spread out. Which is why, when high-speed cars go past you, you hear a sound like that. It's the same with ambulances. Cover your ears when an ambulance goes by, it could hurt your ears, but if you will hear a difference in the note. It goes, Nina, 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 because the Doppler effect. Yeah? Doppler effect. You can look it up online. I don't want to go into it for too much detail because only half of you will need to know it. Oh, but the cool thing about the Doppler effect is it will come up in astronomy as well, because everything in the universe, for reasons which we'll talk about when we do our last module on astronomy, is moving away from us. So stars that are giving off a certain frequency of light, because they're moving away from us, the light seems to be stretched. It's called redshift because the light that reaches our eyes is slightly redder than we would expect it to be. Like, we know what light that star has given off, but by the time it gets to Earth, it's a bit like that. Yeah, because it's moved more towards the red end of the spectrum, the longer wavelength end. So if you want a proper definition of the Doppler effect, it's the apparent change in observed wavelength and frequency of a wave emitted by a moving source relative to an observer. That means the observer is staying still, but the source of the wave is moving. So it seems you will observe that the wavelength and the frequency have changed. It's an apparent change, yeah? Okay, cool. Right, now that you've had a little bit of time to forget some of the things that I told you about before, I can give you this a very brief question sheet to finish off. Just 4 questions here, just to see if you've understood what we've talked about today. You bob a toy duck up and down in a bath, and ripples are produced, right? You bob a toy duck up and down in a bath and ripples are produced. What could you do to change the frequency of the ripples, the wavelength of the ripples, and the speed of the ripples? What could you do to change the frequency of the ripples, the wavelength of the ripples, and the speed of the ripples? And a high note and a low note travel through water. What do they have in common? Are they travelling at the same speed? Do they have the same frequency, or do they have the same wavelength? If a high note or a low note travel through water, what do they have in common? Speed, frequency, or wavelength? And don't forget, over on my Facebook page right now, if you're watching live, is a little post saying you can comment on here if you want to say hello. And I'll say hello to you at the end. If you don't have a Facebook account, well done you, frankly. Well done you. Have you got it? They're probably those questions where you either know it or you don't know it. So you've answered them really quickly, or you are struck and you need me to just help you by showing you. All right, here we go then, let's go through it. What can you do to change the frequency? You could change the frequency of the bobs. You could bob it faster or slower. What could you do to change the wavelength of the ripples? Well, basically the same thing, because changing the frequency would change the wavelength. If you change the frequency, if you'd like double the frequency, you halve the wavelength of the ripples. What can you do to change the speed of the ripples? Well done if you said nothing. You can't do anything to change the speed of the ripples because you're making ripples in water. So unless you change the water, then you won't change the speed. Very well done if you said stuff. Oh, that's a great answer actually. If you said stuff like put more hot water in the bath or put more cold water in the bath, that'd be a really good answer. I don't think it would give it wouldn't give an effect that you would really notice. But technically, yeah, the temperature of the medium does affect the speed. The high note and the low note travelling through water, they've got speed in common because they're both travelling through the same medium and the same type of wave, right? They're both sound waves and they're both travelling through water, so they've got the same speed. They don't have the same frequency or wavelength because, as we've discussed, high notes and low notes, the high notes have a high frequency and low notes have a low frequency. Right. Phew. That is the end of today's IGCSE lesson on wavelength and speed and frequency, and also a little bit of the Doppler effect. I am going to go over to my Facebook page and see if anyone has said hello to me. I should also do my ad to tell you like how on earth these lessons are free. So if you're new, I mean, probably you're not new, but you might be new. Oh, in fact, I've got an ad now made of Lego. Do you want to see it? It's pretty shonky. It's not very good. In fact, it's so bad I might just tell you the ad before I show you the ad. So how this works is, I am trained to teach physics at A-level. I was an actual physics teacher in a school before lockdown happened. And then I started streaming lessons for free. And the home educating community didn't want me to stop. And I definitely didn't want to stop. So yeah, it's all just come together for all of us. There's this website called Coffee, where you can, if people sort of support their favourite podcasts and stuff, people that wouldn't make money from their creative endeavours otherwise. So if you go to the website called Coffee, the link's in my About section on YouTube, you can sign up to support me with £5 a month, and that is what, last time I did a survey, most people are doing it. A lot of people choosing to support me with £5 a month. It's absolutely blooming gorgeous. So everything that I do is free. All these lessons are free. The All Ages lessons are free. The Lego Story Show that I do is free. The printouts of the lessons are free. They're all stored on my website for watching on catch up. I have to pay to store them, but it's worth it because you're paying me. So actually there's quite a good offer on at the moment. But shall I do my ad? I'll do that. I'll do the Lego ad and then I'll go to my Facebook page. Oh, hello, Jacob. On the beach. He's asked me to post because he's currently dodging seagulls. Wow, that is really seagull dodging. Oh, hello, Gus. All right, I'm just saying hi. And Edmund and Bastian and Freya. Oh, and Andrew, hello. Okay, right, I'm going to do my ad and then I'll come back and say hello. I know you all support me anyway. Or you can't, and that's totally fine as well. But I've got to try, haven't I? I've got to try. Here's my ad. You ready? Hi everyone, Lara here from Theatre of Science. Are you enjoying the free lessons that I stream live on Facebook and YouTube? Are you enjoying the vast amounts of hidden and obvious work that I put into them? Here's my kid saying, Mum, do you want to see my sausage roll impression? And me saying, yes, I'm just going to work out how to model the oceans with jam. Are you appreciative of how open access my business model is? For example, I will never ever hold anything back from a child which will let them pass an exam. That is just one of the kind of loose business rules I have in my head, that if it'll help you to pass an exam, I'm not gonna charge you for it. If you are enjoying these lessons and the free printouts and this wonderful, open policy, you can support me with just £5 a month. For the price of a month's worth of cat food. I haven't got a cat, I don't know if that's true. You will receive all my gratitude and also Theatre of Science magazine. Sign up now with £5 a month and you will receive the past issue on mould, which I've written. It's got a home compostable free plastic bag with it that allows you to do a mould growing activity, and it's got comic and choose your own adventure. You will also receive some rainbow glasses in the post and an explanation sheet. I wrote about how they work. This is all for £5. And if you support me with £6 a month, then I've got a special offer on at the moment. You will receive this past issue on sleep, which comes with a little sleep squish pack so you can do some sewing. It comes with a beautiful sleep magazine, but also just for a short period of time, I'm also throwing in a third magazine. I'm throwing in the magazine that I wrote about weeds because it's got a slight misprint. Some of the words in it are ever so slightly blurry, like still readable, but just a bit blurry. So I'm throwing in this third magazine. It's only for people who sign up with £6 because otherwise the £5 supporters would be getting more than they paid me, if you see what I mean. But I can just about afford to put in the Weeds magazine for free. So you actually, if you sign up now, you get 3 magazines and the rainbow glasses and the instruction sheet for £6. And then the idea is that the money just keeps coming out per month and that pays for the lessons. And when I've written a new theatre science magazine, which takes me ages, you will be on the list to get the next issue. Thanks, bye! That's my ad. That's my Lego ad. Hope you enjoyed it. I need to write a script for it. But, you know, it's all a work in progress. Right. What's everybody saying? Okay, so this is great. You're all doing completely different things. Jacob is dodging seagulls on the beach in St. Ives. Jacob, you are making being on the beach at St. Ives look really... Oh, so I've lost my little bit of Lego that I used to prop up my camera. You're making being on the beach at St. Ives look... Oh, no, actually. No, I thought you were going, oh, no, the seagulls. No, you're just eating something. You look like having a really nice time. Oh, God, it looks so sunny. Oh, I'm so jealous. What's everyone else doing? Gus is busy doing outdoor pursuit adventures at Ardentini. Might be paddleboarding, might be orienteering, who knows. I've escaped the nearby botanic gardens. We'll watch on catch up. Oh, I was thinking, how is Gus doing all that and watching this? Gus, you're going to watch on catch up. Gus taking a little bit of time out from his Chicago Youth Theatre endeavours to do some orienteering. Amazing. How do you have to... I do still feel when Gus is around that I'm one of those like educators that has to help celebrities get their IGCSEs just in case their film career doesn't work out. Edmund is watching live! Yes, Edmund! Oh, you've been watching Veritasium. Oh, I love Veritasium. Which explains why light changes speed as it moves into a different medium. Oh, that's brilliant! Oh, that's perfect, thank you. If anyone is interested in finding out about this in greater detail, the video is called Why No Two People See the Same Rainbow, and it's even linked to it. Amazing. Says you could change the speed of the ripples by adding something to the water. That is brilliant. Like something to make it thicker. Yeah, that's a really, really good point, yeah. So changing the medium, basically, yeah. Very good point. Yeah, like a bath bomb. All right, Bastian, hello. Freya says she likes the sweet diagram. Oh, thanks, Freya. Thanks. Yeah, it's a very common problem, I think, in physics, that people just think if that changes, then that must change. But that's not how it works. Same with, if you did electricity, same with V equals IR. It's like, it looks really simple, but it's actually not. And there's A at the end. Ah, lovely. Well, thank you. That's nice to see all your comments. And for those of you that are still watching but have not commented, hello to you too as well. Very much appreciate you still being here. Makes a huge difference. I always say, if everyone lurked, it would be rubbish. And if everyone commented, it would also be rubbish and unmanageable. I need you to all just do exactly what you're doing right now. Okay, right, I'm going to go. Yeah, how nice. This was my last lesson of the day. I don't even have to rush off and gather soil or anything like that. Just going to go. Maybe just do some not speaking for a bit. I hope you had a nice time. I definitely did. We've only got 2 more lessons left and then it's the summer holidays. 2 more lessons left on waves. And then after the summer holidays, we're going to start a whole new module on energy. So, but I'll see you next week because we've still got 2 more. Bye!